Okay, thank you for the introduction. And I would like to thank organizers for organizing this amazing conference and for giving the opportunity to speak here. I will tell you about my recent work on vertex operator algebras that I've done with Davide. And also I will comment on some work in progress together with Tomáš Procházka. So just to remind you, vertex operator algebras are chiral algebras of chiral operators in two-dimensional CFT with the algebra structure given by operator product expansion. Some of the familiar examples are Virasoro algebra associated to stress energy tensor, which is following OPE. This algebra has parameter C, which is called central charge, and I will talk about it later. Another example is Kac-Moody algebra that is associated to conserved currents in two-dimensional CFT, and components of these conserved currents have following OPE, where there's a constant K, which is called level of the Kac-Moody algebra in this case. And another example are WN algebras that are extensions of algebra of stress energy tensor by fields of spin 3, 4, 5, and so on up to n, together with U1 generator J that I will include for the purpose of this talk. These algebras appear at various places in physics and mathematics, such as AGT correspondence, geometric Lagrange, and many other places. The main goal of this talk will be to give find vertex operator algebras that appear at trivalent junctions of interfaces in N equals 4 super Young Mills, and this setup actually has lived to string theory, and in the past always when we found a lift of some system to string theory and used dualities of string theory and various other insights that string theory gives us, it very often led us to interesting point of view on the objects that we are interested in. And I will use those insights in order to look for dualities for vertex operator algebras. I will shed some light on dualities that are already known and conjecture many new dualities. And as a byproduct, I will also explain and give explicit construction of truncations of W infinity algebra, and also tell you how to use a topological vertex-like construction to construct more complicated vertex operator algebras from simpler algebras that we called Y-algebras. So let me first describe the Brane setup within which we will realize those vertex operator algebras. So let me consider trivalent junction of D5, NS5, and 1,1 Brane in type 2B string theory. And let me attach 3 stacks of L, M, and N D3 branes as shown in the picture. Note also that the point where all the branes meet is two-dimensional, and that will be exactly the place, the corner, where vertex operator algebras appear. The low-energy theory of N D3 branes can be identified with N equals 4 super Young Mills with UN gauge group. And from the point of view of those D3 branes, we can think of this configuration as trivalent junction of interfaces between UL, UM, and UN gauge theories. So starting from the Brane setup from the previous slide, we ended up with the trivalent junction between UL, UM, and UN, N equals 4 super Young Mills. And in this talk, we will concentrate on Kapustin-Witten twist of the theory. N equals 4 super Young Mills is a supersymmetric theory that admits several twists, and in particular there is a family of Kapustin-Witten twists, and different Kapustin-Witten twists of N equals 4 super Young Mills are labeled by parameters, continuous parameter psi that will play an important role in our story. We can see that at the corner of the at the corner of the diagram, vertex operator algebras appear, and we can see that following 2 steps. Firstly, by a variation of argument made by Witten and Mikhailov and Witten, one can argue that path integral for the N equals 4 super Young Mills in this setup localizes to the path integral of UN/L Chern-Simons theory at level psi, induced at NS5-like boundary. together with UM/L Chern-Simons theory at level psi plus 1 induced at the 1,1 brane boundary. Those two Chern-Simons theories are glued together by boundary condition, and this boundary condition can be deduced from the work of Gautav and Witten on boundary conditions in Habib's boundary conditions in n equals 4 super-Young-Mills, where they give explicit construction of boundary conditions that come from the descent from D3 branes ending on various phi branes. So what we have done, we followed this construction slightly more carefully, and we associated to each numbers of branes L, M, and N the following vertex operator algebras. There are combinations of Drinfeld Sokolov reduction and coset of UN/L Kac-Moody algebra. In particular, what do I mean by the right-hand side of the equation or the definition of Y-algebras? One is supposed to start with UN/L times UM/L Kac-Moody algebra, add a bunch of goes that are necessary for the two BRST reductions that I will describe in the second and third step. In the second step, one is supposed to perform Drinfeld Sokolov reduction that I label as W of the Kac-Moody algebra. And roughly speaking, the Drinfeld Sokolov reduction fixes upper triangular part of n minus m times n minus m diagonal block inside one of those two Kac-Moody algebras. And one is supposed to do that by looking at cohomology with respect to the operator that fixes this constraint. The third step is the coset step that I label as a division by UM/L. And by this coset, I mean gluing the UM/L Kac-Moody algebra with the other diagonal block of UN/L. And we have to do it again by the BRST procedure. In particular, let me give you an example how those constraints really look like, how the construction will look like for n equals 5, m equals 2, and l equals 2. So we start with two Kac-Moody algebras, J and J tilde. In the first step, we need to take 3, where 3 is 5 minus 2. So we need to take 3 times 3 subblock of one of those two algebras, and constrain upper triangular part of this block together with some components of the diagonal block, something I don't have time to describe. And in the second step, one is supposed to glue this J tilde with the other empty diagonal block of the J's. Let me be slightly more technical and give you show you really explicitly how the calculation works for U2 Kac-Moody algebra. So we start with U2 Kac-Moody algebra. This is generated by the following currents, satisfying following OPEs. And we want to fix the upper triangular part, which is J plus equal to 1. This constraint can be implemented by the following BRST charge, where I had to introduce a ghost C, which is part of the BC ghost system with the following OPE. If one sits down and compute the cohomology with respect to this BRST charge, one finds out that the cohomology is generated by generator J and this combination of fields. And if one computes OPEs of those two fields, one finds out that the resulting algebra is actually U1 times the Virasoro algebra, and the central charge of the Virasoro algebra is given by the following formula. Let me give you 3 comments before actually going to applications of the string theory insights. The first comment is that the algebra that we got from this construction in this Drinfeld reduction is invariant under the change of psi going to 1 over psi. The duality is sometimes called Feigen-Frenkel duality, and essential element to see, Feigen-Frenkel duality. And this duality is far from being obvious before we actually did the calculation. There actually exists another third realization of the same algebra based on the following coset, where one starts with 2 copies of U2 Kac-Moody algebras together with a pair of fermions, One looks at the cohomology of the following supercharge that roughly glues the two U2 factors. And one obtains the same Vertex algebra with the same central charge. Again, something far from being obvious. Let me also know that the coset G/H from the previous slide can be is basically the same one as described here, just without the fermions, and in the case where J1 is restricted only to the components in one of the diagonal parts. It's arbitrary complex number. It's arbitrary complex number in the sense as we are using this. The question was if psi can be arbitrary complex number. The answer is yes, it can, and it has to do with the fact it's basically analogy of the complexification of Chern-Simons theory due to Witten from 2010. Okay, so let me summarize the explicit example that I told you about. There are three realizations of Vertex algebra in terms of these two different philosophical reductions and a coset. And there actually exists analogy of these constructions for UN algebras, where there are, again, three realizations. And yeah, in this section, I will explain this duality and conjecture many new dualities using S-duality of our configuration of branes. So S-duality of type 2b gives rise to SL2Z duality action on PQ interfaces in N equals first Rapcak-Mills, and it also transforms parameter psi as follows. It is generated by transformation T and as written on the slide. It is interesting to know that there is S3 subgroup of this S-duality group that preserves the trivial junction and simply permutes the three interfaces. This duality action induces S3 action on Y-algebras, and one can conjecturally identify algebras like those algebras, where apart from the change of the coupling constant, we also permuted the indices and LMN. Diagrammatically, if one starts from one configuration and performs TS transformation, one changes the coupling constant as follows. The branes get permuted, but one should also realize that by rotation by angle 120 degrees, one can move the picture into to have the same orientation that was used for definition of Y-algebras, where NS5 brane is pointing upwards and D5 brane is pointing to the right. And one can simply deduce that the dual algebra is the one from the previous slide, which corresponds to permuted labels LM and N, and transform parameter psi. T is what? TS? No. It's this transformation. It's one of the generators of the SL2Z S-duality transformations. Okay, let me give you some examples. If we set L to 0 and M to 0, one recovers from our triality exactly those three well-known realizations of WN algebras. But there's much more. If we set L to 0, M to 1, and N to 2, one recovers three realizations of parafermions, where the first construction is quite well known, the other two is slightly less well known, but already constructed. But there are also many other dualities that we haven't found anywhere in the literature, and by plugging in other integral numbers, one can recover these sorts of dualities. What we have done for general L and M, we have checked that central charges and vacuum characters for those algebras indeed matches, supporting this conjectural triality. There's another perspective that one can have at those Y-algebras that we introduced, because they can be identified with truncations of W infinity. So W infinity algebra is algebra generated by fields of spin 1, 2, 3, 4, 5, and so on up to infinity. And Gabriel and Gopakumar imposed Jacobi identity on the algebra of such spin content, and they found that Jacobi identity fixes all the parameters except of two, one being central charge, another being some other parameter in some OPE. And they call the two-parameter family of vertex operator algebras W infinity. They also realized that at special lines, ideal in the algebra appears, and if one quotients out by this ideal, one recovers Wn algebras. Moreover, they found a triality action on the parameter space, and that's why we actually get 3 different colors associated to each algebra. Later on, Tomáš Procházka studied the truncations more carefully, and he actually found many more truncations that didn't have any construction, and it was unclear what are those objects. What we found is that those other truncations can be actually identified with Y-algebras that we have introduced. And moreover, the triality that we have found when translated into the parameters of Gabriel and Gopakumar turned out to be their triality. The last comment or application that of Y-algebras that I want to talk about is that those can be thought of as atomic elements for constructing more complicated vertex operator algebras by construction similar to the topological vertex construction. For example, let me consider the following diagram of resolved conifold, and let me attach K, L, M, and N, the 3 branes from the 4 corners. By a similar argument as before, we can argue that there are 2 Y-algebras associated to the 2 corners. But also, there exists physical argument that one should extend those vertex operator algebras by bimodules associated to the line operator stretched between those two vertices. And the resulting vertex operator algebra associated to such a diagram should be some conformal extension of the following of the 2 Y-algebras. Even the simplest diagram of resolved conifold seems to be very interesting and seems to describe large family of vertex operator algebras. Moreover, those vertex operator algebras will have Z2 times Z2 duality, which can be deduced in the same way as we deduce the duality or the triality of the Y-algebras. And these Y-algebras turn out to be truncations of an analog of W infinity algebra with the following vacuum character, where parameter rho is half integral number, and there are 2 special cases where rho equals to 0. One recovers truncations of W1/1 plus infinity. When rho equals 1/2, one recovers truncations of n equals to W infinity algebra. So it seems that actually by this gluing procedure, analogous to topological vertex construction, one can construct many new possibly interesting vertex operator algebras. So let me conclude. I have defined those vertex operator algebras, Y-algebras, associated to trivalent junction of interfaces n equals for Surpe-Young-Mills. And I employed S-duality to explain triality for Wn algebras as a consequence of S-duality. I gave generalization of this triality to 4-parameter family of Y-algebras. As a byproduct, I gave explicit construction of truncations of W infinity algebra. And I told you that Y-algebras can be thought of as building blocks of more complicated vertex operator algebras via topological vertex-like construction. It would be nice to explore the vertex operator algebras associated with more complicated junctions further. We have been working on that, but there's still a lot of things to be done. And also explore the analog of the story for orthosymplectic groups by including O3 planes parallel to the D3 branes. Moreover, I hope there will be applications to many other problems in mathematics and physics, such as AGT correspondence, counting of D0, D2, D4 bound states, spiked instantons, geometric Langlands program, ADS3, CFT2, and many other places. Thank you for listening.